Atoms are made of other particles. As you can see, atoms inside the atoms, we have neutrons, protons, and electrons. The protons are positively charged particles found in the core. Look, we see that we have them in this picture noted with red circles. Neutrons are uncharged particles also found in the nucleus. They're denoted by purple circles. And in this picture, we have electrons, which are negatively charged particles. They are not found in the nucleus. Instead, they're in the outer area, and they have a negative charge. Since in a neutral atom, we don't have a charge, that's because the number of protons and the number of electrons are the same if it is an atom. We also have things called ions, in which case the protons and electrons are not the same, and we will need to talk about them soon, but for now, let's stick to atoms. So if we look at these particles, electrons, we're going to say they have zero mass. They actually do have some mass, but it's so small as to be insignificant. Imagine if you put a cup of coffee on a car, the cup of coffee is not going to really change the mass of a car by very much. It has a -1 charge. Technically, we don't measure charge just in units, but it's in coulombs, but we say that it's -1 to make it easy. And they're located in orbitals or the outer area. They're not located in the nucleus. If we move on to protons, protons have a mass of 1 AMU. Their charge is +1, and they're located in the nucleus, the core of the atom. And then when we talk about neutrons, they're also mass of 1 AMU. If you look at the grams of a proton and a neutron, they're not identical. The neutron is just a tiny bit heavier than the proton, but we just say that they're the same mass and they're both 1 AMU. The neutron has no charge, and it is located in the nucleus. So what happens if we gain or lose an atom? Again, we've spent a lot of time in other classes probably talking about atoms, and in this class we are going to have to talk about ions a lot. So I want you to understand that the only thing that really can change in an atom is the number of electrons. Because they're in those orbitals far from the nucleus, we can remove electrons and add electrons to an atom and make ions. But for protons and neutrons, they're in the nucleus, that tight core, they cannot be moved. So you can find an atom with a certain number of protons or a certain number of neutrons, but you can't change it without a radioactive decay mechanism. So we're going to say in chemistry class, the number of protons and the number of neutrons in a given atom are fixed. You might be able to find different atoms with different amounts, but you can't change it once you find that atom. So let's look at a lithium atom and a boron atom. And you might look at these and say, how do I know it's lithium? How do I know it's boron? Well, the element is determined by the number of protons that are in the atom. So on the left, you see 3 protons indicated by those red circles with positive signs in them. And that means this atom has an atomic number of 3, and lithium has an atomic number of 3. So atomic number refers to the number of protons. Because it has 3 protons, this is lithium. It also has 4 neutrons. Now remember, we said the electrons don't have much mass, but the neutrons and the protons both have a mass of about 1 AMU. So if I count up how many protons I have, which is 3, and how many neutrons I have, which is 4, 3 plus 4 is 7. So this would have a mass of 7 AMUs. Note also, because it's an atom and it's neutral, I have 3 protons. I also have 3 electrons with the blue circles with the negative signs in them. On the right, we have boron. Notice immediately one thing that's different about boron and what makes it boron is that it has 5 protons in the center, whereas it still has 4 neutrons. It also has 5 electrons because in an atom, which is neutral, it must have the same amount of protons and electrons. If I look on a periodic table and look for the element that has an atomic number 5, that's boron, and so I know that this is a boron atom. If I wanted to know the mass, I would have to add up the protons and the neutrons. So I count 5 positive protons in red, and I count 4 a little bit hidden, but we have 4 purple circles for neutrons, and 5 plus 4 is 9, so this would have a mass of 9 AMUs. Now we also have things called isotopes. Isotopes are considered to be 2 atoms that are the same element, so they have the same number of protons, but they have different numbers of neutrons, and therefore they'll end up with a different mass. So on the left we see sodium 22 and sodium 23. The 22 and the 23 are telling me their mass. And if I count up, although they're kind of hidden in there, I'll notice in both cases there are 11 protons, because sodium always has 11 protons. So you kind of have to dig around, but there are 7 positives on the left and 7 positives on the right of those 2 sodium atoms. On the left, I have 12 neutrons. 11 protons plus 12 neutrons equals 23 AMUs, and so I show a mass number of 23 AMUs with that symbol. On the right, I have 11 protons and 11 neutrons. 11 plus 11 is 22, thus I have a mass of 22, which is shown above the chemical symbol. In the lower corner, I have 2 isotopes of carbon. I have carbon 12 and carbon 14. Here we could probably do a better job of counting. You have 1, 2, 3, 4, 5, 6 protons, which is associated, all carbon atoms will have 6 protons. And on the left, you can't really tell, they're kind of hiding one another, but there's also 6 purple circles. And I know that because I'm seeing that there's a mass of 12, and 6 plus 6 has to equal 12. On the right, I still have 6 protons because it's carbon, and I have 7 neutrons, or 8 neutrons, and 6 plus 8 is 14. Okay, so as you've already started to see, we have isotope symbols. And in an isotope symbol, I have a chemical symbol. In this picture on this slide, I have that indicated by the SY. On the upper left of the chemical symbol, I have the mass number. And again, the neutrons and the protons both are things that contribute to the mass equally. So I'm going to count the number of protons and count the number of neutrons, and I'll get a mass number. Note that it has to be a whole number. I can't have 0.2 protons. So I have 1 or 2 protons. So when I count up my protons and neutrons and add them up together, I get a whole number, and that will be my mass number. And that is the mass number for that one atom. On the lower left, I have the atomic number, which is the number of protons in the atom. Note that I kind of don't need to have the atomic number and the chemical symbol because they're sharing the same information. If I use a periodic table, the symbol has the atomic number shown, and so if the atomic number is 6, which is the atomic number of carbon, I can either show carbon, the chemical symbol, or 6 for the atomic number, and both supply the same information. But you don't get to shortcut. I do. For you, you always want to write the atomic number in the lower left and the chemical symbol. You have to include both, even though they are redundant information. So if I needed to determine the number of neutrons and I knew the mass number, I can do some subtraction. The mass number is the number of protons with the number and the number of neutrons, and the atomic number is just the number of protons. So if I take the mass number and subtract off what are due to protons, what's left must be what's due to the number of neutrons. So as I look at this symbol with Ag, and it has a mass number of 109 and an atomic number of 47, 109 minus 47 equals 62. And here's a good time to point out that the mass number has to always be bigger than the atomic number. That top number should be bigger because it's the number of protons and neutrons, whereas the bottom number is the number of protons. If the top number were smaller than the bottom number, that would be impossible. So when you're looking at an isotope and you're checking your work, make sure you should have a bigger number on the top than on the bottom of your isotope symbol. When we convert isotope symbols to number of protons, neutrons, electrons, this is how it looks. Again, I get to shortcut and write just 13C, which we would say, if we're looking at that symbol, we usually pronounce that as carbon 13. We say the chemical name first, and then we report its mass number. So carbon 13. It can also be written carbon-13. But in isotope symbol format, we would show the 13 in the upper left corner and C next to it. Immediately, I can look up the number of protons from the atomic number. And I usually always want to start with protons because that's fixed by what element it is. So I go to a periodic table, I find carbon, and I look and see it has an atomic number of 6, which means that the number of protons is 6. I can determine, now that I know that, I can determine the number of neutrons. The mass number, 13, minus the atomic number, 6, is 7, and that's the number of neutrons. Remember, the mass number is the number of protons and neutrons. And the atomic number is the number of protons. So I'm just subtracting off how much of the 13 was due to protons, and what's left has to be due to neutrons. If it is an atom, then the number of electrons has to be the same as the number of protons in order for it to be uncharged. Remember, the protons are positively charged, the electrons are negatively charged. So in this case, it's 6. However, don't forget that atoms can form ions by gaining or losing electrons. So in the case of sodium, if it loses one electron, it becomes sodium with a positive charge because now it has more protons than electrons, and I'm going to see that as a positive charge. Positively charged ions we call cations. Below that, we see aluminum. Aluminum loses 3 electrons and becomes aluminum with a 3+ charge. Again, it's a cation because I have more protons than electrons now, and so I have a positive charge. On the left, we see chlorine. Chlorine can gain an electron. Because it has more electrons than protons, it has a negative charge. And sulfur can gain 2 electrons. It has more electrons than protons, and therefore it has a -2 charge. And negatively charged ions we call anions. So a good question that we will handle in a future chapter is, why does sodium lose 1 electron and aluminum lose 3 electrons? And why do sodium and aluminum lose electrons where chlorine and sodium gain electrons? And why does chlorine only gain 1 electron but sodium gains 2 electrons? And we are going to handle that in a future chapter, but there are certain elements gain, certain elements lose electrons, and they tend to gain or lose a specific number of electrons. So we do have this concept called average atomic mass that shows up on the periodic table. When you look at something like chlorine and you look underneath, you find its atomic number is 17, and you also see a mass number of 35.5. Not a mass number, an average atomic mass of 35.5. Now, how do we go about calculating that? We've been playing with these mass numbers, and we said that the mass numbers had to have a whole number. So how do you get a decimal in your atomic average? Well, this is a kind of like your class grades. Although there's no actual chlorine atom with a mass of 35.5 AMUs, I'm averaging out the masses of all the atoms. So if I look at a sample with millions of chlorine atoms, let's suppose I just had a sample of chlorine that had just 4 atoms. I'll never find such a small sample, but if I did, and I looked at them, and 3 of the chlorine atoms were isotope 35 mass, and 1 was isotope 37 mass, I could just do this like I do all my averages, 35 plus 35 plus 35 plus 37, add them all up, divide by 4, and I get 35.5 AMUs. But if I wanted to now look at a sample of 12 million atoms, I wouldn't be able to count them, and I wouldn't be able to do that. In that case, I need to look at the weighting or the abundance of the mass 35 chlorine to the mass 37 chlorine. So if it turns out that 75% were mass 35 and 25% were mass 37, which actually is about what I'm expecting if I have chlorine, I have to do something called a weighted average. This is, by the way, how I also calculate your grade, so it's handy to know how to calculate a weighted average. The fact is, I can't just take 35 and 37 and add them together and divide by 2, because I have a lot more 35s than 37s. So I must weight the 35 by how often it shows up. I'm going to take the percentage and convert it to decimals, so 75% becomes 0.75, and multiply it by 35. And that would be the portion of the mass that's due to the chlorine 35 isotope. The next term is I have 25% of chlorine 37. I convert 25% to 0.25 in blue, and I multiply it by the mass of the 37 chlorine, which is 37, and I get that portion. Once I'm done with all of these isotopes, I add all the totals together, and I get 35.5 AMUs. Now, it's already been calculated for you based on, they find samples, they measure how many percentage are of one isotope and how many are another, and in many cases we have elements that have 5 or 6 isotopes. So they run mass spectrometry, they determine the natural abundance of each isotope, and they calculate this, and this is the non-whole number that appears on the periodic table, which we call the average atomic mass. Note that it does not tell me the mass of any one atom. It's only useful for telling me, on average, how much would one atom have. If I had a collection of billions of them and I wanted to have a representative, that's what it would be. So again, let's do a separate example. This one is silicon. Silicon has 3 isotopes, mass number 28, 29, 30. Now in reality, the actual mass of the atom is not 28, 29, and 30. It's slightly less, and there's some details to why that I'm not going to go into. But I take the isotope mass, and I'm going to multiply it by the abundance for each in decimal form to get the proportion of each one. So on silicon 28, I convert 92.23% to 0.9223 and multiply it by its mass, 27.976927. For mass number 29, I take the 4.67, I convert that to to decimal, and I get 0.0467. And I multiply it by the mass, 28.9, ... And then for the mass 30, it has a 30.1% abundance. I convert that to decimal, 0.031, and I multiply it by its isotope mass, 29.97, etc. When I finished multiplying these, remember I have to multiply first. After I multiply, then I add them together. I get 28.08. And if you look on the table for silicon, you find that that is about what the average atomic mass that's shown on the periodic table. We'll try some problems here. So go ahead and try these, and after you finish this video, I will post the answers.